Last year, a mysterious ring of fire was spotted in space thanks to Albert Einstein's theory of relativity. Researchers believe the ring was an illusion created by the light of two distant galaxies. One 12 billion light-years away, and another 4 billion light-years away. Now, a new study of the image has revealed that a dwarf dark galaxy is hiding in the halo of the larger and closer galaxy. The ring was created by a phenomenon, called gravitational lensing, which was predicted by Einstein's general theory of relativity. It can shed light on the properties of the nearby lensing galaxy because of the way its gravity distorts and focuses light from more distant objects. In a new paper accepted for publication in the Astrophysical Journal, scientists from Stanford University in California explain how they uncovered signs of the hidden dwarf dark galaxy. We can find these invisible objects in the same way that you can see rain droplets on a window, explained astronomer Yashar Hazav. You know they are there because they distort the image of the background objects. In the case of a raindrop, the image distortions are caused by refraction. In this image, similar distortions are generated by the gravitational influence of dark matter. Current theories suggest that dark matter, which makes up about 80% of the mass of the universe, is made of as yet unidentified particles that don't interact with visible light or other forms of electromagnetic radiation. Dark matter does, however, have mass, so it can be identified by its gravitational influence. For their study, the researchers harnessed thousands of computers working in parallel for many weeks. They wanted to search for subtle anomalies that had a consistent and measurable counterpart in each band of radio data. The computers helped them able to piece together an unprecedented understanding of the lensing galaxy's halo. This is the diffuse and predominantly star-free region around the galaxy. They discovered a distinctive clump less than 1,000th the mass of the Milky Way. Because of its relationship to the larger galaxy, estimated mass, and lack of an optical counterpart, the astronomers believe this gravitational anomaly may be caused by an extremely faint, dark matter-dominated satellite of the lensing galaxy. The work could lead to the discovery of more collections of dark matter and also solve a long-standing discrepancy that has baffled astronomers. According to theoretical predictions, most galaxies should be brimming with similar dwarf galaxies and other companion objects. Detecting them, however, has proven challenging. Even around our own Milky Way, astronomers can identify only 40 or so of the thousands of satellite objects that are predicted to be present. This discrepancy between observed satellites and predicted abundances has been a major problem in cosmology for nearly 2 decades, even called a crisis by some researchers, said Neil Dalil of the University of Illinois, a member of the team. If these dwarf objects are dominated by dark matter, this could explain the discrepancy while offering new insights into the true nature of dark matter, he added. Computer models of the evolution of the universe indicate that by measuring the clumpiness of dark matter, it's possible to measure its temperature. So by counting the number of small dark matter clumps around distant galaxies, astronomers can infer the temperature of dark matter, which has an important bearing on the smoothness of our universe. If these halo objects are simply not there, notes co-author Daniel Moroney of the University of Arizona, then our current dark matter model cannot be correct and we will have to modify what we think we understand about dark matter particles. This study suggests, however, that the majority of dwarf galaxies may simply not be seen because they're mainly composed of invisible dark matter and emit little if any light. Our current measurements agree with the predictions of cold dark matter, said team member Gilbert Holder of McGill University in Montreal, Canada. In order to increase our confidence we will need to look at many more lenses. Our next step is to look for more of them and to have a census of their abundance to figure out if there is any possibility of a warm temperature for dark matter particles.